Okay, I left us 12 minutes to talk about Newton's third law because it's very important. Okay, we got to spend some good quality time together on Newton's third law. A couple of problems I didn't get to, I will put online, so you'll have access to them. But you know, Newton, important guy, came up with 3. We don't want to shortchange him and give him a 67. We want to do all 3 of his laws here. Let's see. Oh, look at all that. Okay, so Newton's third is also one that you can kind of recite. Wow. I've never seen that much hype over Newton's third law before. This is kind of one that you can just say to yourself. Let's all say it together. For every action, there is an equal. I can write as fast as you can talk. And opposite reaction. See, I told you I could write faster than you can talk. We've all heard that. I heard Newton's second law in a commercial this morning on TV. They actually said it. What commercial? It was something, I don't know, it was like an insurance commercial or something. For every action is equal and opposite reaction, but action was Newton's way of saying force. For every force, there's an equal and opposite force, is really what it means. Okay? So the key is all forces are interactions between 2 things, only 2. Every force we've talked about, I could tell you the 2 things that are interacting. Okay? So we call those action-reaction pairs. The forces are action-reaction pairs. So for example, when the block sat on the table, right, we talk about a normal force up on the block. The block applies a force down on the table. And it has the exact same amount. The normal force up equals mg, the mass of the block, times g. The table feels a force equal to mg, the mass of the block, not the mass of the table. When the rope pulls on something, there's a tension force applied here, and there's a force applied to the rope. That's why the rope has tension. Right? It always works out that way. Okay? So let me just get the screen, because there's something you need to be able to see. I'm sure it's going to give me trouble. All right? Because what we're going to do is we're going to demonstrate Newton's third law. Okay? And there's one ultimate best way to demonstrate Newton's third law. That's going to eventually come on. This doesn't recognize me with my glasses on yet. All right, hold on. The best way to demonstrate Newton's third law is with arm wrestling. Okay? So I usually bring down a football player and arm wrestle them. But the football team is in Hawaii. Poor babies, right? So I thought, what glass-jawed punk at Rice could I come up with to arm wrestle? And I have the ultimate Dr. Danico. And let's see, he's going to stretch a little. This will eventually be a poll where you can answer the question. What we're going to think about as Newton's third law is whose palm is going to feel the most force once this arm wrestling match is over. And that's what you can vote on if the screen comes up. Okay? Okay, hold on. Ready? All right, we're going to get right here. So are you right-handed or left-handed?
I'm right.
So quiet in here. Okay, you're righty, I'm lefty. Or you're right? Okay, here we go. Now let's think. Oh, it's not coming up. You got to think about whose palm is feeling the most force. You ready? Go. Ah! He got me. Thank you, Dr. Danico. Thank you, Dr. Danico. No, the screen didn't come up. That's all right. So think about for a second. I think I can get this to come on. I think I can get this to come on. Y'all can be voting. Just we'll give you 1 minute. Whose palm felt the most force in that brilliant display of masculinity? I'm sorry for the masculinity on horrible display here. Okay, you can't vote. Let's do a virtual, let's shout out the answer, right? So you're either going to shout out Danico or Hafner. Whose palm experienced the most force in an arm wrestling match? 1, 2, 3. Same. Oh, you guys are so smart. Damn Rice students. I can't have any fun with you guys. But this is a case where you got to think about Newton's second law, or Newton's third law, right? So I said the palm of your hand, right? So this was Danico's palm, and this was my palm. The force between them was the same. But what's weird is the whole thing accelerated, right? Why did the whole thing accelerate? It's because Danico's arm is just a little stronger than my arm. Right? Okay, so the net force on the whole object was not balanced, and that's why the whole thing accelerated this way. But the actual pressure between them, the actual force between them was equal. If I put a spring scale between our hands, it can only have one reading. It's not going to say, well, the force over here is big and the force over here is small. It's a spring scale. It only can press a certain amount. So the force in between is the same, but it's the force of the rest of our bodies that makes the big difference. So the last thing I'll say then about these is when you're asked to find action-reaction pairs, people find it very difficult because they're mixing it up with Newton's second law, N2 and N3, right? So let's think about a quick table that will help you do these problems. Not that we give that many of them. But Newton's second law, how many forces do you deal with in Newton's second law? 0 to infinity, right? In Newton's second law, you're getting the acceleration of an object. It can have as many forces as you want on it, right? In Newton's third law, you're only dealing with 2, right? So this is forces, and this is objects. How many objects are you thinking about in Newton's second law? 1. How many objects are you thinking of in Newton's third law? Always 2. When you're asked to find action-reaction pairs, you are not summing the forces on an object. You're thinking about the interaction between 2 objects. What are you calculating when you do Newton's second law? The acceleration, usually, right? You're trying to get the acceleration. What are you calculating when you're doing Newton's third law? Nothing. You're not calculating anything. Why do we do Newton's third law? If it doesn't calculate anything, why do we even bother? Is because we're IDing forces. It helps us ID forces. It helps us find them, and it helps us get their magnitude. Okay? So you have one homework problem where you're thinking about some stacked boxes, right? And I forget what it is. I think it's the boxes are all sliding or something, and you got to think about the forces these boxes are applying to each other. Well, you might be good at calculating, okay, what's the normal force that these apply to this? Okay, well, it's N. Well, you say, well, what's the normal force this applies to this? It's also equal to N. So it's a way to get the magnitudes of all the forces by checking that any 2 things pushing on each other, it has equal and opposite forces. Okay. Let me just answer these leftover questions and then we can stop. I didn't know how long that would take. I thought I would last longer, but class has to end early. Let's see. Why is the pulley on the right? Here we go. Why is the pulley on the right have mg from the wall if it is in the x direction, not the y? Oh my God, that's such a genius question. Let me make this very clear, because you'll be doing a lot of tension problems, so you definitely want to know this. The genius question is, I said, where did it go? Oh my God, did I erase it? It was I think I erased it. It was this. It was, we had the wall with the thing on it, and going around that, and it had a mass. And we said, why is this force mg? It's not in the right direction. It's not a weight force. It's the tension force pulling that equals mg. It's the tension, and I'm just telling you its magnitude equals mg. And the reason it can go this way is that's what a rope does, is it takes the tension as a scalar quantity and it applies it in whatever direction you want, right, to the things it's attached to. So if I want to apply gravity sideways, I get out a pulley, I string a rope over it, I put a weight here, and I apply gravity sideways. That's what the rope is for. Last one. Why am I rushing? Did you cut your sleeves? Yeah, I cut my sleeves. Where do you think I shop? It's like, yeah. Okay, so I'll see you Tuesday.